All right. Kevin, can you see Fort Charlie?
I can see the screen. It's the preview PowerPoint. All right, it's full screen now.
Okay. We're good to go. Okay. We talked about antennas. We talked about feed line. Now we got to talk about how we connect them together. The typical connectors that are used in amateur radio are called a PL259 for the male connector and an SO239 for the female connector. They typically label them as UHF connectors, but they're not. They're really only good up to VHF. For VHF, for higher VHF, UHF, people normally go with N-type connectors, which are a little better as far as an impedance match. They're somewhat moisture resistant. They seal. I wouldn't say they're waterproof, but they're also quite a bit more expensive.
But I've also seen a lot of people talking about you need some rubber tape when you make
Yes.
a connection to go around it.
Yes.
That helps seal it off.
Yeah. You definitely need to, for external connectors, you need to waterproof them. And we'll talk about that in a little bit. There's also BNC type connectors, which is a bayonet type, where you push it on and twist it and it locks. You see that on test equipment, oscilloscopes and signal generators and things like that. Some of the smaller QRP radios will use bayonet BNC connectors because they're smaller for one thing. It's a quick disconnect. There's also an SMA, which is a very small, about a quarter inch.
Now I use that to hook to my antenna, and I could hook to this radio. No, there's not one there.
No,
That's me.
no,
No,
no. That's a
it's a little old thin, got the little bitty. It's got the screw that it's got the screw on the end that you can screw, take this antenna off, and you can screw it onto this radio. Then the other end that I've got is got a 259 on it, and I can hook it to my exterior antenna and use this.
that's 259 mated to this little.
I was talking about to the little USB.
Oh, you're right. That is an SMA
There's one
connector.
there. It sure
Yeah.
is.
You see those used inside equipment a lot to run little short runs of coax for signals between one board and another.
We also use the TNC a lot. Is that you guys don't really see a lot of that in
Don't see it in amateur radio much.
Got those connections on, like, I've got a antenna analyzer and it's got those connections.
Which SMAs?
SMA.
Yeah. The little nano VNAs have SMAs on them. Most of them. Now there is a version that has SO239s. And I think they have one with N connectors, but they're a little bit bigger.
Well, my power meter's got N connectors on them. But it came with adapters for
Yeah.
the other too.
And the N's are the best if you're doing UHF. They claim they're waterproof. I guess I believe them. I'm not sure. And looking at them, how they seal that well, but that's what they claim. The
Well,
problem
that-
is,
It's got that inside piece in
Right.
those.
right.
So I guess because of.
But the other problem with them is that inside piece is much closer to the center conductor. So they will arc over at about 1500 volts, where a normal 239 is about 3000.
I don't think I'm gonna be pushing that, but.
Well, now see, you obviously don't think about what kind of voltages you can get on an antenna. or connector.
Hmm.
The end of a half-wave dipole at resonance can be over 3,000 volts. Maybe higher. In fact, if you're feeding the antenna with 100 watts, that's 70 volts RMS that you're putting on the antenna at the center.
That high voltage, a lot of things will
Yeah. Here's a picture of kind of the assortment. The SMAs are good up into the multi-gigahertz range. The end connectors are up, I forgot what they rate them at. Probably 10. I'm not familiar with the TNC, but it's I think just a variation of the end connector.
The smaller one.
Yeah, these are not to scale.
Here's
Yeah. Because the end connector is more than twice as big as this SMA. And then we have these little MCXs. I don't know if you've seen those. These are very, very small.
SMC is just the same thing as a SMA, but it's a female instead of a male, or is it?
I'm
That's what
not
it
sure.
looks
I think well, I don't know. I've never used one, so I can't say. The MCX you will find inside of a laptop, for instance, possibly a cell phone. It's a little snap-on connector. These things are maybe a 16th of an inch.
I've got one of those.
for little GPS, for like small GPS receivers.
I got one of those on SDR.
There's a typical BNC bayonet connector, another SMA type. I don't know what the B version is. It's not a reverse SMA, which is what you probably have on that radio. Is that a Chinese?
Both fine.
Yeah, it's got a reverse SMA as opposed to a regular SMA.
Yeah, I have to put a barrel on it.
Yeah. And then down here, we have our PL 259, which is good up to 300, 350 megahertz, even though they call them UHF connectors. So which of the following is true of PL 259 type connectors? Yep. People use them at UHF, but it's not optimal. Which of the following RF connector types is most suitable for frequencies above 400 megahertz? Bravo. Because they left out SMA.
Yep.
Some people have trouble putting connectors on coaxial cable. And if you haven't done it a lot, and if you don't have the right tools, yeah, it can be a pain. One of the causes of failure in feed lines is if you have very high SWRs running a lot of power and you have fairly high loss coax, you get enough heating to actually cause damage to the coax.
Well, all you have to do is ohm it out. You ohm out the outside from one end of the cable to the other, and then you ohm out the inside, make sure you have no short. Then you should be good to go.
Yep, should be. Unless you have a little braid wire that's almost in contact, and then when you put enough voltage on there, it arcs over.
It would show up on the ohm meter either.
Nope, it wouldn't show up on ohm meter. And the arc would vaporize a little piece of wire. Unfortunately, it would leave a little metal trail, so you'd always have a low resistance path.
That wouldn't eliminate your problem.
You need to make sure that connectors are tight. They can, with vibration, particularly going up to an antenna where it gets vibrated around in the wind, they can work loose. So you need to check them every so often.
That's where your rubber tape around that connector helps a lot too.
It'll help, yes. It can cause some very erratic SWR readings if your connectors are not tight. And also it allows water in, which is another reason why you tape them. The best way I found is you use plastic electrical tape, the 3M, I can't remember the numbers, is it 33? The straight one, which stretches and bonds itself pretty good to cover it. Then you use the rubberized, which 3M also sells. Now you can buy an amateur radio version at probably twice the cost, but it doesn't work any better than the 3M stuff you can get at Home Depot. And it's a stretchy rubber that bonds to itself, so it kind of molds. And then you cover that with tape because that rubber is not UV tolerant. So that's why you use the regular tape on top of it to protect it from UV. You put it on as a first coat because if you put the rubber tape directly on the connector and you have to take it off, it's a god-awful mess because it sticks. So if you put a layer of tape on first, then you just slit it with a knife and you peel it right off.
My antenna's got that. It sits down inside of the pipe that holds it up. So it's on the inside of that, but it's still not waterproof though.
Right.
Because moisture can still get
Right. You can get condensation in there. So what can cause erratic changes in SWR? Bravo. Sure. It's Black Rifle, so you might want
the
green.
good stuff.
It's Beyond Black, it's called. We talked a little about SWR, standing wave ratio. It's kind of a measure of how well your antenna is matched to the transmission line. So ideally, you want to have them a perfect match, which means it would be 50 ohms. In the real world, you're not going to find many antennas that are 50 ohms. So we need to do some sort of matching or antenna tuner, which doesn't tune it. We'll talk about that a little bit. The SWR, if you're perfectly matched, should be 1-to-1. So a really good match system, you're going to read an SWR of 1 point something. You'll never actually see 1-to-1 in the real world.
unless you're good at adjusting them, huh?
Well, even then it can change.
Well, it's gonna change with the frequency too. Is it not?
The SWR won't. Well, I shouldn't say that.
Because you're gonna have more the higher
At
you
a
go.
different frequency, your antenna is going to operate differently. So if you've got a multi-band antenna, you need to have it matched for each one of the bands you're operating on. If you're at a single band, like a straight half-wave dipole, it's only resonant at a small portion. It's actually resonant at one frequency, but you're only going to have a low SWR for a very narrow band of frequencies, and typically it won't cover that entire band. So if you were wanting to do voice, you'd be on the upper part of the band, and then you decided that you want to go down and do FT8, which is like at the very bottom of the band. In tuning down from one to the other, one of those is maybe going to be resonant. Well, the other one isn't. You're going to have a much higher SWR.
Yeah.
Just in a few hundred kilohertz. Because typically your bandwidth isn't that wide.
And that really comes into play for the 10-meter band. You guys are gonna have access to the 10-meter band. So you have to pick if you're gonna build an antenna, you need to pick your range, which the FCC has already done for you, because they say you can transmit between 28.3 and 28.5. So that gives you a nice narrow range right there to target 28.4 for your antenna when you build an antenna, and you should have that whole portion covered. When you upgrade to general, you've got what, 28.3 up to 29. So
Well,
that's
28.0.
not voice.
No, but
Yeah.
they could operate from
Yeah.
the whole 28. So they can do CW and digital down at the bottom.
So that's really wide. It would be tough to get a single band antenna that's gonna cover that much width without a.
So I'm gonna have to put up 3 or 4 antennas to cover frequencies.
You know, get a.
Well, you don't have to.
Yeah, don't have to.
You could,
Yeah, that's what the tuner's for.
Yeah.
yeah. Or you can go to something like an in-fed half wave where it's resonant at multiple bands. It's resonant at even and odd harmonics. So you can have one wire antenna that operates pretty good. I mean, you won't have a perfect SWR, but you'll be below 1.5 on almost every band.
My primary antenna at home is the ARRL kit for the 40 through 10. It's a 66-foot wire stretched between a palm tree and an oak tree. And that thing tunes everything from 40 to 10 effortlessly.
The downside is it's a fixed position.
Yeah.
I mean, you can't rotate it.
Yeah.
Let's see. SWR 1.5 is usually considered acceptable, even up to 2. Beyond that, you're really not getting much power in or out. And above 3, normally the transceiver is going to start reducing your power to protect itself. If you're interested in the math part, there's different ways to calculate SWR, and it's the ratio of the load impedance to the source impedance. So if you know that your antenna is 75 ohms and your transmitter is 50, then your SWR is approximately 1.5. And that's all your SWR meter is doing, is that kind of calculation, usually by just the scales. If you've seen any, and I think there's a picture coming up here. Seen any of the cross meter needles, where it actually has 2.
Yeah.
One is forward power, one's reflected power. And where they cross, they'll have little lines etched that are different SWRs. And that's all those lines on there are calculated based on the ratio of the powers. So what is standing wave ratio? It's a lot of things, but it's basically how we measure how well we're matched. What reading on an SWR meter indicates a perfect impedance match?
Charlie.
Would be nice to see that. What does an SWR reading of 4-to-1 indicate?
You're in trouble.
Like a
D.
a D?
Delta.
It's usually like you got short or something.
Or your
Bad, man.
way off resonance. If you look at an SWR plot for an antenna, when you start getting very far off resonance, you'll see 10, 20, 100 SWR. reading. So SWR is going to be low if you've got a good match. It's going to be high when there's a bad match. I mean, it's simple. If the SWR is low, it means that your signal losses are low. It means most of the power, the forward power, is getting to the antenna and not being reflected back. When it's high, it means you've got a much greater reflected power, which is power that's being reflected from the antenna back. And then it kind of keeps going back and forth until it either is dissipated in radiation or in loss in the cable. Actually, both. Less power to the antenna, less radiated power. This is showing your blue line as the signal going to the antenna. We have a reflection coming back, which is kind of small. In this case, it's the red wave. But when you add that to the blue, you get the black line. And this is what you see as a reflected wave on the coax. And that's what comes back and what the transmitter sees. What's the benefit of a low SWR? Bravo. What happens to power lost in a transmission line?
Charlie.
Charlie?
Converted to heat.
Like I said, most of the modern transceivers will reduce output power. That wasn't true of the older tube type because they were much more tolerant and didn't need to do it. Could operate into a much higher SWR. Transistors are not quite so tolerant. And usually it's at 3-to-1. And that's why most of your transceivers that have a built-in tuner, it'll only tune up to 3.1. And it's not actually tuning, it's doing matching.
That tuner has got a coil of wire in there. And the distance between, and that's what it's doing, is doing like this.
Well, usually they're doing taps or they have multiple inductors and they're
Right.
picking them. And it's usually a pi network where you have a shunt capacitor, a series inductor, and another shunt capacitor. And you adjust all three of those. In the automatic tuner that's in a radio, the processor in there is doing that, and it's kind of trying different combinations and looking at the SWR, and it keeps doing it until it gets down to as slow as it can go. If you're doing a manual tuner, you do the same thing, except you have to control all three knobs. So you tweak the inductor, and then you go adjust the input capacitor, and then this one, and you try it again to see if it's better. You keep, doing it until it's the lowest you can get. It may not be a 1-to-1 match.
But as long as you're under 3.1, you're good.
Well, yeah. Normally would try to get much better than 3. Why do most modern solid-state transceivers reduce output power as SWR increases above a certain level? Alpha. When choosing an SWR meter, okay, you want to make sure that it'll operate over the frequency range that you want, because they'll normally specify it may only be HF, or it might be a VHF, UHF. You normally wouldn't find one that covers the entire range.
Right.
Also power. A lot of times they'll only go up to say 200 watts. Well, if you're operating a external amplifier and you got 1,000 or 1,500 watts, you need to make sure that you've got an SWR meter that'll handle that kind of power. Now, most of the power amplifiers probably have a built-in SWR meter, but not necessarily.
Would your tuner be able to tune?
On the radio,
Yeah,
well, that's only tuning what it sees as the antenna, and you've got a power amplifier there now, which should look like 50 ohms. So you should have a perfect match between your radio and the power amplifier. But it's between the power amplifier and the antenna that you need to do the match. Because you have a high SWR coming back to the power amplifier, you're not necessarily going to see that effect back on your radio. There shouldn't be much kind of bleed through effect.
A lot of the modern radios have a tuner and SWR capabilities built right into the radio. But as soon as you put that power amp on there,
you change everything.
yeah, change it, yeah. So you can't use the internal SWR or the internal tuner.
It's not gonna give you the information.
Okay, so and we kind of talked about all this. There are some SWR meters that will indicate forward and reflected power separately, like some of the digital ones or the cross needle type. There's some that just measure SWR. They don't tell you what forward and reflected power is. A couple examples. This is a digital one, and it shows SWR as well as forward and reflected power. This is a cross needle type. It does the same thing analog, where you actually have to read where the needles cross.
Is that sometimes called a birdie?
No, you're thinking of a bird watt meter, I think.
Okay.
That's the kind of standard. They're not cheap.
Yeah, I know they're not cheap.
Yeah, everything we have at the shop at work is bird brand.
Which of the following should be considered when selecting an accessory SWR meter?
Oh,
Okay. You can also measure SWR with a directional watt meter, which just reads out like the bird. It reads out forward and reflected. At least the one I've used only indicates forward, and you rotate the knob to measure reflected. It shows one or the other. It doesn't do SWR. But you can calculate SWR from forward and reflected with this little formula, which is basically the ratios of forward and reflected power in that formula. It looks more complicated than it is. It's fairly simple to plug in the numbers. And you need to make sure that you put your SWR meter in the feed line between the transmitter or power amplifier and the antenna. Which instrument can be used to determine SWR?
that'd be Delta, wouldn't it?
Yeah. Where should an RF power meter be installed?
Talk about that. Alpha.
Okay, antenna analyzers. I was going to bring one, I didn't. They can be used to measure SWR of an antenna system. Actually, what they measure is the impedance. Well, a number of things, but they can measure the vector impedance, which is what they call it a vector network analyzer. There are some instruments, MFJ makes a number. Rig Expert outfit from Ukraine makes some very nice antenna analyzers. They're not cheap either.
They know they're nice.
Well, I got an antenna analyzer, the little black one.
Nano DNA.
Yeah,
Yeah, okay. And when you measure the SWR, you're doing a sweep of frequencies for the antenna. The lowest point on there is where it's resonant. Now, that may not be 1-to-1. It's just going to be the lowest point. If it was a half-wave dipole that was up, so it's going to be around 72 ohms. When you see the resonant point, it's still going to be a 1.5-to-1 SWR, even though that's the resonant point, because it's 75 and you're feeding at 50. So in order to get that SWR down, you need a matching network, okay, to convert the 50 to 75. Or if it was a different type of antenna, it might be a couple hundred ohms or a few thousand ohms, like for an infid. So you use balance or ununs, which are basically transformers to match it. If you're using something like the nano VNA or a regular laboratory type VNA, it can measure the capacitive and inductive reactances. You can also use it as a signal generator because it can generate a frequency signal. In fact, that's how they work. They put out a sweep signal and see what comes back. So they can be used to do a lot more things than just checking an antenna. In fact, I use mine because I messed up and I made a 3 or 4 foot jumper cable out of LMR 400. And somewhere on one connector, I wound up with a piece of a wire from the braid that got wrapped around the center conductor that I didn't see. So after I got it all put together and ohmed it, it was a short. Well, which end was it? Which connector do I cut off? Well, it turns out you can use a nano VNA as a time domain reflectometer. So you set it up in that mode where it just sends out a pulse and it shows how long it takes for the reflected pulse to come back. So when you connect it to the shorted end, there's no time. When you connect it to the other end, even though it was only 3 feet away, you can see the difference and tell which end has the short.
That's very nice. Yeah, I would have saved you a lot of things.
What about Smith chart? Now, what is a Smith chart showing?
Smith chart shows you in resistance and reactance,
Okay, so
basically.
when I do my Smith chart, sometimes I get a circle,
Yeah,
and then sometimes that circle is
have a lobe or something.
yeah.
Okay. The circle, all right. You don't need to know this until the general.
I'm jumping ahead, but
A Smith, are you familiar with, I was talking about rectangular coordinates? Okay, where you have an x-axis and a y-axis. Okay, and we plot things, vectors. Okay, we plot resistance on the horizontal axis. We go from 0 to infinity. Okay.
okay, that's when your marker is the circle, and then
Well,
your
we're not
marker
to a
is-
Smith chart yet. We're just going to plot resistance between 0 and infinity. We're going to pick a point in the middle and say that's 1. So we've got 0 to 1 to infinity. So obviously it's a logarithmic scale. Okay. You follow me?
Sort of, yeah.
All right. Now we need a vertical axis. Okay. So at 0, I'm going to draw a vertical axis. And I'm going to say that the positive portion of that axis is J X, or which would be X sub L, the inductive reactance. It's positive. On the bottom, the negative side, I'm going to plot capacitive reactance. It's negative. Okay.
Okay.
So if I was to measure an antenna impedance, it's going to come back with Z is equal to some R value, say 50 ohms, plus some reactance value. So say I get 50 plus J50. Okay, so I go over 50 on the resistance scale, and I go up 50 because it's plus. Okay, so I plot that point, and that vector from 0 up there is the impedance, the magnitude of that. It's longer than 50, right? Okay, that's how you basically plot impedance and on a rectangular coordinates. Now this guy Smith decided, well, since we're going from 0 to infinity, and we're going from 0 to infinity plus, and we're going from 0 to infinity minus, I can define infinity this, infinity that, all meeting at the same point, right? So this curves around and meets the resistance infinity, and this one curves around and meets the resistance infinity. So I now have a circle with the horizontal line. So that outer circle is positive reactance and negative reactance. And they all meet at infinity over here. And they all cross at 0. Okay?
Okay.
So what would normally have been a vertical line, okay, is now curved out to infinity. So instead of 1 ohm, I've got a reactance circle that goes to infinity. At 10 ohms, I've got another one. At 50 ohms, I've got one. Okay, so those are called reactance circles on the Smith chart. So anywhere on that circle, the reactance is the same. Just like if it was going straight, okay, the value wouldn't change. So the other thing that he did in order to use it for different impedances was when we defined 1 in the middle, instead of that being 1 ohm, we normalize everything. So if we're going to work with 50 ohms, we divide whatever measurement we have by 50, okay, and plot it. So if it was 50 ohms, then it would be 1 on the horizontal axis. If it was an impedance or a reactance of 50, it would be 1 on the reactance axis. So that's all he did was figure out how to convert a rectangular chart into a round, kind of a polar chart. So when you see, like on your nano VNA, if you make a measurement and you display it as a Smith chart, and you see that circle around there, it means that's I think I said a constant reactance. That's a constant resistance at different frequencies. The reactance is changing, but the resistance is not. Because the resistance part is typically just the actual resistance plus the radiation resistance. Whereas the reactance changes a lot. So as you change the frequency, you will see that circle.
Because my circle, I'm trying to build me a scanner antenna.
And when that circle crosses the horizontal line, that's where it's resonant.
Okay, so my circle goes, it's going around, and then down here it does a little jig jag and then continues.
Yeah.
So I was curious about that. Uh,
Okay. Yeah, we were way ahead of ourselves.
okay.
But Smith charts are neat. You can do a lot of things with it.
Yeah, I started looking at it and all that math in there. I'm like, oh, there's my meter right there.
Right there. That's a nano VNA.
Yep.
And over here is a MFJ antenna analyzer, one of the older ones, I think. But it pretty much gives you just analog readouts on the meters. The rig expert actually will draw graphs. I don't know that it can do a Smith chart, but it will do a sweep and show you an SWR plot.
Mhm.
But they're
So the round circle you see it in there, that's the Smith chart.
right,
Yeah.
right. Which of the following is used to determine if an antenna is resonant at the desired operating frequency?
Problem.
We beat that one to death.
Mhm.
Said we beat that one to death. If an antenna's impedance is not 50 ohms and the impedance at the transmitter end is not going to be 50. It's going to be a reflection, an impedance conversion. So you need the antenna tuner. It's in quotes because I'm not sure where the term came from. It has nothing to do with tuning the antenna. It's strictly a matching network to try to match the impedance. And actually what you're doing, I talked about the impedance being a vector, which is resistance plus reactance. The matching network does what we call a conjugate match. In other words, it generates the opposite reactance. So if you had impedance of 50 plus J50 in the matching network, you would come up with a 50 minus J50, and it would cancel out the inductive reactance that you were seeing. So that's how it quote tunes it. It just is doing a conjugate, what we call a conjugate match. This is a little QRP type where it's manual, and the knob on the right is changing the value of the inductance in the pi network, and these other two are variable capacitors. So you have to play with all three. And it has a switch in there so you can bypass it or tune it. And you see this one for small QRP stuff is using B and C connectors. What's the major function of an antenna tuner or coupler? Alpha.
Alpha.
Okay. The next thing is a dummy load. They're used to basically simulate an antenna for troubleshooting or tuning purposes, where you can operate into the dummy load without actually transmitting. So you can do adjustments on your transmitter without actually sending out signals over the air and having to do your ID and stuff like that. So you could even do that unlicensed as long as you were radiating into a dummy load. Dummy loads are typically 50 ohms, non-inductive, so they have no they're not supposed to have any reactance. So it should look like 50 ohms across the whole frequency range. They'll have a power limitation. In this one, I think this is the same one I have. It says 300 watt dry dummy load, which means there's no oil and there's no fan. It's good for 300 watts for a few seconds. It's good for 100 watts for maybe a minute. So you have to look, and in this one, there's a chart on the back of it that shows you, how long you can operate at different wattage ratings because they're just heating up the resistors. So you can get bigger ones. I also have a can antenna, which is like a gallon bucket filled with oil and a bunch of resistors in it. It's good for like a kilowatt or more. Oh. And basically, they define the dummy load as a non-inductive resistor or resistors, because it's usually more than one, mounted on some sort of heat sink.
So the antenna, the oil is a heat sink.
Awesome. Yep.
What does a dummy load consist of?
Rob.
Okay, so we learned about PL259s and type N connectors and SMAs. Loose connections can give you a high SWR reading and some other bad things. A perfect match would be a SWR 1-to-1, which you're not likely to actually see, but you see maybe a 1.1, 1.05, which is really, really good. The lower the better, the higher the not better. And that your transmitter, if it's a new transistor type, is going to automatically start reducing power when it sees a high enough SWR, typically around 3-to-1. You use an SWR meter. You need to make sure that you get one that has the appropriate frequency range and power level. You may need more than one. If you want to use one on VHF and UHF, that's probably all it measures. And an HF one doesn't go up normally to UHF and VHF. So if you do both of those things, you need at least 2 SWR meters if you want to measure SWR. You can use a directional watt meter to do it, where it measures forward and reflected power. There, you don't necessarily have to care what the SWR is, just watch how much reflected power. So you want to have a minimum amount of reflected power. Located between the transmitter and the antenna. Use the antenna analyzer, measuring SWR, reactance, a bunch of other things. Antenna tuners are just matching networks, and use your dummy load to avoid transmitting on the air when doing testing of your equipment.